I'm Pat Shahan from the AUTOBOT team. This is my team member, Andrew Dolby and Jacob Steele. Our project is to develop an autonomous control system for the 2012 Lunar mining robot. Essentially, this project is a NASA competition in which we will be mining simulated lunar soil, or lunar regolith, with the eventual goal of having fueled missions into deep space or lunar bases. One way we'll be doing this is, or implementing this autonomous system, is with the use of Kinect. We'll be using this for object detection and obstacle avoidance, and it allows us to use depth data captured by this camera to see obstacles. Andrew Dolby will be talking a bit about robotic localization.
The automated part of our system is going to be navigation. In order to achieve points in the robotics competition, we can automate various processes in order to achieve points for each individual process that we automate. Navigation gets us the most points, so that's what we focused on. The robot uses this Sequoia rangefinder here in order to get its position, and there are algorithms that we've implemented, including a particle filter, to tell the robot where it's at initially, because the robot can start in various positions in the competition, and also its orientation, because the robot can start in various orientations, and the robot needs to know where it's at. Jacob will talk a bit about the platform that we use for testing, and also about mapping.
The platform we used for testing is a iRobot Create. Our sensor network will be built such that the laser rangefinders will be placed one facing forward and one facing backward, so that we can see basically as the full 360 view of the walls. The Kinect that Pat had earlier will be placed facing forward again so that we can see obstacles in front of us. As far as the software side, we use a dynamic mapping algorithm, and basically this system can work on any number of chassis, and basically it'll drive forward until the connector tells us that there's something in front of us, whether that's a hole or a rock, and our algorithm will basically just try to avoid. It'll go around it. The reason it's dynamic mapping is it starts off with a clean slate. It assumes there's nothing in front of it basically, and then as it moves forward it keeps looking forward. Is there something in front of me? Is there something on the horizon? And this creates a very efficient algorithm. We don't have to worry about some of the space issues you might have with larger, more complex algorithms. And it also has one benefited note for efficiency. It goes straight. It doesn't try to veer, it doesn't try to explore. It basically finds the fastest route it can. It doesn't do backtracking, it doesn't try to plan the best path. It literally just brute force finds the quickest route. And so this will be utilized in the Lunabotics competition, and we'll hopefully get our team some added bonus points. That is it for our design. Thank you very much.